case for FRQ 8A, so average net force, so the net force is equal to M times A. Now we know then A, we could break it up to change in V over T. And since we know that in this scenario, so there should be A here. So it should be M times, so we know we can plug our numbers in since we know it. So we know our M here is going to be 0.5 times 20 minus 0, because it starts at 0, it goes to 20, and that's all done in 0.05 seconds. And as a result, the answer should be 200 newtons. And that will be our net force for the thing. And it's at a 37-degree angle. So 37 degrees of the plus x axis. Okay, so for 8b, we're trying to find the time it takes to reach there. So we could say the time it takes to reach there is equal to the change, that's the displacement over the Vx. And then we know in this case, Vx is just going to be Vi cos of 37. And then, so we could plug numbers in. So it has to move 32 meters horizontally over 20 cos 37. And if you simplify that, you should get about 2.003 seconds. And that'll be the time it'll take to reach. So for the next one, we have to find the velocity at that point. So first, Vy of t, I'm going to write it as the initial velocity minus 9.8 t. This is Vy. We know it's just Vi sine 37 is minus 9.8 of t. And we plug in 2.03, which is the time it takes to reach it. Which then we plug it in, so it should be 20 sine 37 minus 9.8 times 2.003. In this case, it will be negative 7.5 meters per second. Then we know in this case, the Vx is going to be constant throughout it because there's no other force that's going to be acting it in the horizontal. So now we can write this. So we define the Vt squared is equal to Vy of t squared plus Vx of t squared. So we have V of 2.003 squared is equal to Vy of 2.003 squared plus Vx at 2.003 squared. So we know this one here is going to be, so then that means, then we square, so we know V of 2.003 squared is equal to negative 7.5 squared plus 20 cosine 37 squared. And then if you square root everything, after you square root everything, the velocity, the speed at that point will just be 2.003, will be 17.69 meters per second. But now we have to find the angle. So just arctan of the Vy 2.003 over Vx of 2.03, and you plug that in, the angle should be 25.44 degrees below the positive x axis. And so it will be 17.69 meters per second, which is our speed, and it will be 25.44 degrees below the positive x axis. So if we look at the real 8D, we are trying to find the speed after it was in 2 meters above. So I can just use common form. So Vf y squared minus Vi y squared is equal to 2g delta x. In this case, So then 2g delta x, negative 2g delta x, because g is going to pull it down. So then it's vfy squared is equal to viy squared minus 2g delta y in this scenario, actually, not x, my bad. And then, so then we can just plug numbers in. vfy squared is equal to 20 sine 37 squared minus 2 times 9.8 times 2, which is how much it rises. Then we square root all this. And if you square root it, you should be getting 18.99 meters per second. And this will be the speed at that when it rises 2 meters above. So for 8d, you just find the change in y. It's equal to viy t plus 1/2 at squared. In this case, change in y is equal to 20 sine 37 times t, which is 2.003, minus g over 2 times 2.003 squared. That means our change in y will be equal to 4.45 meters. And now if we subtract that from the 2.5 meter height, we find out that it's actually at that, when it reaches that plane, it will be 1.95 meters above it. So it will not hit that, but it will just be above it. Answer for F, which is the horizontal vertical component drawing and the graph. We're going to graph it. So the horizontal component is going to be the same. So it's going to be about 16. And it's going to be that for the whole entire thing because there's no other acceleration in the horizontal plane. But then in contrast with the vertical component, we start at 12. So about here. So you see here, 16 is about up here-ish. And then 12 is right here. And at 2.03 seconds, we're at negative 7.6. So we go here, then we go about negative 7.6 right here. And if we draw this, we can say this, we know that the slope, oh shoot, that's a bit off. Yeah, it's a bit off, but approximately, so if we draw it carefully, and it should be like this. Then the block that we're in this, well, the projectile will experience acceleration 9.8 meters per second squared, negative 9.8 meters per second squared on the vertical, in the vertical plane. Fine for 8e. So we're trying to find what angle we should be launching it. So what we had to do here is first write out our function. So we're going to do range function in this scenario because it's asking for the bottom of the fence, which is most likely here, or unless it's talking about up here. So we know tangent x is equal to vi squared sine 2 theta over g. Then we just isolate for sine 2 theta. So delta x times g over vi squared is equal to sine 2 theta. Then we could just arc sine it. So we have 2 theta. So arc sine of delta x g over vi squared. Then we could divide by 2. So our theta will just be equal to arc sine of change in x g over vi squared. And this whole arc sine is divided by 2. Then we just plug in, so that we know the change in the displacement is just 32 times 9.8 over vi squared is 20 squared. And if you do all that, the answer should come out to about the answer should come out to about about 51.63 degrees above the positive x-axis.